An everyday item that we all take for granted, magnets. But how do they work? What is a magnet? Come with us on a journey if you want to find out.
Magnetism is a force that acts at a distance and is due to a magnetic field. This magnetic field is caused by moving electron particles and is inherent in every magnetic object, such as iron, nickel, and cobalt.
But what about copper?
No, not copper.
Oh.
Magnets have two different poles, a north and a south. Opposites attract. Now, when we have two similar poles, like a north and a north, they repel. Remember, opposites attract and likes repel.
Hey Regan, I found it!
Oh my god, Katie, are you okay?
I found a magnet, but now it's broken.
Oh, no, don't worry. When you break a magnet, it doesn't break into two halves, creating a magnetic monopole. It just breaks into two smaller magnets, which both have a north and south pole.
So there are three main types of magnets: permanent, electromagnet, and temporary magnets. Let's start with the permanent ones. How do they work?
Permanent magnets are the most common type in our daily life. These magnets are permanent in the sense that once they have been magnetized, they retain a certain degree of magnetism and do not lose it easily. They are made of ferromagnetic material, which consists of atoms and molecules that each have a magnetic field and are positioned to reinforce each other. Examples include the magnets on your fridge. To understand why permanent magnets work, we have to look at the atomic level. We all should know from chemistry that protons are positively charged and electrons are negatively charged. Well, we know electricity and magnetism can be converted much like matter and energy, as you'll see in the light video. We also know that electrons are much bigger than protons and are 1,000 times stronger magnets. Therefore, they will affect the magnetism of the particle. You can think of each electron as a tiny magnet with a north and south pole. We know this because every particle has a property called its intrinsic magnetic moment that basically tells how magnetic it is. So these tiny magnets form in shells or groups around the nucleus. Filled shells of electrons have poles that point in opposite directions, canceling out and therefore lacking magnetism. This can be seen in elements such as manganese. However, in an unfilled shell of electrons, magnetic poles line up, giving the overall atom in a magnetic pool. This can be seen in elements such as iron, cobalt, and nickel.
Well, that's cool, but what about when you put a magnet on an unmagnetic object, such as a nail, and it temporarily becomes a magnet?
Temporary magnets are those that simply act like permanent magnets when they are within a strong magnetic field. Unlike permanent magnets, however, they lose their magnetism when the field disappears. Examples include paper clips, iron nails, and other similar items are examples of temporary magnets. Sometimes when ferromagnetic material is arranged in the right way, such as in cast iron, you have domains of magnetic particles all pointing opposite directions and canceling out. This can demagnetize the iron. However, if you expose the demagnetized iron to a strong outside magnetic force, the domains temporarily align, forming a temporary magnet until the domains return to their original positions.
Okay. So earlier we said that electricity and magnetism were related, so can you use electricity to create a magnet? Electromagnets, mate. Electromagnets are extremely strong magnets, mate. They are produced by placing a metal core inside of a coil of wire carrying an electric current. The electricity in the current produces a magnetic field. The strength of the magnet is directly proportional to the strength of the current and the number of coils in the wire. Its polarity depends on the direction of the flow of the current. While the current flows, the core behaves like a magnet. Consider a copper wire. It's not a permanent magnet, but it's a great conductor of electrons. These electrons in the copper wire cancel out with the positively charged metal ions and make a neutral wire. However, when the electrons begin to flow, and if a charged particle were to move with the flow, then the particle would be repelled because relativity causes unequal positive and negative charges in the wire. This would seem mysterious to a bystander because the charged particle is repelled from a seemingly neutral wire. From the particle's frame of reference, it is being repelled by an electric field from the uneven charge distribution in the wire, but from the bystander's frame of reference, the wire has moving electrons making it an electromagnet, so the particle is being repelled by a magnetic field that runs around the wire and perpendicular to the flow of electrons.
Hey Regan, did you see that new TV show on last night?
No, but I can tell you what factors affect the strength of an electromagnet.
Really?
Really?
Huh.
Number 1.
Increasing the number of coils of wire around an object can increase the strength of the electromagnet.
Number 2.
By using a battery with a greater voltage, strength is increased. And by adding more batteries to a series circuit, you can increase the strength as well.
Number 3.
An iron core will produce the strongest magnet. Increasing the size of the core can also increase the strength of the electromagnet.
Wow, Regan, that sure beats the TV show I was watching last night.
I know, it's pretty awesome, isn't it?
It's so awesome.
Note: because paper is only two-dimensional and magnetic field is three-dimensional, our drawing has certain symbols to represent the three dimensions. The X's represent the magnetic field going into the paper. The force vector is pointing out of the magnetic field, while the velocity vector is pointing right, making all three perpendicular.
While we're on the topic of charged particles, we might as well discuss how to calculate the force of a magnet on a charged particle in motion. This is given to us by Lorentz force law. It says that F equals QVB sine theta. F is the force of the magnetic pole. Q is the charge of the particle in coulombs. V is the velocity of the particle in meters per second. B is the strength of the magnetic field in teslas. And theta is the angle from the path of the charge to the magnetic field in degrees. The force is perpendicular to both V and B in the third dimension.
Electromagnetic induction utilizes the relationship between electricity and magnetism to create electricity. If a conductive coil of wire is moved in a magnetic field, a charge is produced in the coil, creating electricity. This is basically the opposite of how electromagnets work. An electromagnet is formed from a current that creates a magnetic field around the conductive wire. While electromagnets use electricity to create a magnetic field, electromagnetic induction uses a magnetic field to create electricity. Whoa! Ryan! Whoa! Stop! Put me down here, please! Over here! Okay, thank you. Now we can continue. We can see electromagnetic induction at work if we take apart a motor like this. A motor uses coils of wire that rotate around magnets. When current is flowing through the wires, they become an electromagnet and repel from the permanent magnets, creating a circular motion. However, if we turn the motor by hand, it does the opposite and becomes a generator by spinning coils of wire around the permanent magnets. This causes the dislocated electrons in the wire to flow and produce a voltage, as you can see on the multimeter.
Magnetism. It's a force for you and me. How it really works like electricity. It's not always something you can easily see, so just take a minute and watch me. A magnet has two poles, south and north. Put them together and forces go forth, 'cause opposites attract and likes repel.
What happens if it breaks?
Well, they're both still magnets with poles again. There are three simple types, I'll make them plain. Temporary, permanent, electromagnet. Let's learn some more so you can have it. Knowledge I mean, which I hope you glean from this mean rhyming machine. Permanent magnets you see every day. They're the ones on your fridge.
Really? No way.
Magnet number 2 is temporary. Now these types are a little bit scary, 'cause you never quite know if they'll work or not. But in a magnet field, don't give it a thought. Electromagnets, now these you know, only work with electron flow. Like this sick beat that I'm dropping right now. Here's a scientist telling us how.
Electromagnetic induction. Wahahahaha.
Bring the beat back. The motion of charges of common bar magnet is constantly moving, though magnet be stagnant. This makes up a current which causes a field that acts to attract an opposite pole. That's how magnets work, I already told. But what you might not already know is how you can get some of the flow of electrons to move from kinetic to volts. Electromagnetic induction results in currents that form from magnets in motion. I really hope that you're getting the notion that it's connected to the third type we named. Electrons, it's all the same. Transformation of energy points out which is which. Induction or not depends on the situation at hand and what you start with. But now you know they can easily switch.
Oh,
K out.
Yeah, KTP in the house.